an approach to the reverse dictionary task based on automatic smart subword segmentation of Ukrainian physical texts. Maksym, Vakulenko, Vadym, Slyusar. Introduction. A significant aspect of natural language processing tasks involves the generation or prediction of text or words. Reverse dictionaries hold promise in this domain, where machine-generated lexical units are proposed based on their definitions. Within this framework, employing subwords as fundamental linguistic units offers notable advantages over conventional methods. Compared to approaches using complete words as the smallest units, utilizing subwords circumvents issues associated with unseen words, allowing for the construction of new words using an existing subword vocabulary. Unlike character-based approaches, subword employment maintains a connection to underlying semantics. It is important to highlight then that the prevalent byte pair encoding method for word segmentation, grounded in mathematical statistics, exhibits several drawbacks. Among these, the most unpleasant is its tendency to erroneously segment compound words like electron-neutral as electron-neutral, or so instead of electro-neutral. At the same time, one of the major difficulties in the terminology work is conditioned by the need to process huge amounts of terminological data, which motivates their automated processing. In particular, an important part of terminology management is the prescriptive step where the prescribed or recommended term should be chosen or created on the basis of its definition. In this sense, the process of attributing designations to concepts in terminology science corresponds to reverse dictionary task in NLP. Such formulation of terminological and, more generally, linguistic tasks in terms of machine algorithm contributes to linguistic competency of an artificial personality with artificial intelligence that manifests the person's ability for human-like thinking, effective lingual communication, and the so-called accurate report. The last is considered, in turn, a significant sign of consciousness in mammals. Little work of this kind has been done heretofore on the data coming from low-resource languages such as Ukrainian. This paper aims to address this gap by employing symptomatic statistical and analytical methods from the field of terminology science. The segmentation of Ukrainian texts relies on the set of Ukrainian morphemes, affixes, sourced from specialized dictionaries. A curated collection comprising 2,000 Ukrainian roots, encompassing both commonly used and domain-specific units, has been manually introduced. Our initial approach involves the utilization of individual subwords. The subwords exhibit significant homonymy, wherein the same combination of letters may occur in different parts of distinct words with varying meanings. We anticipate that incorporating individualized subwording into the neural network will yield average sense embeddings similar to those at the word level. Then, as an analog to contextual embedding models for words, we elaborate on a vocabulary of combined subwords, wherein each sense corresponds to a combination of elementary subwords, if applicable. We hypothesize that this second approach will yield a more specific neural network output. The definitions and explanations of terms are drawn from the explanatory dictionary on physics, which, after the removal of in-text cross-references, comprises over 6,000 distinct entries. The resulting subword vocabularies contain approximately 1,000 units each. The free Microsoft transliteration tool has been utilized to facilitate automatic text segmentation based on rules embodying both approaches. To range the predicted terms according to their applicability, we suggest using the apt term criteria formulated in a machine-friendly manner. Exactness, the concordance between the term meaning and its morphological structure. Essentiality, coverage of key aspects of the concept and absence of false association. Plainness, a clear inner form of a term. Derivativity, the ability to easily create derivatives of the word. Good sound, the agreement with phonotactic rules. Systemic feature, or reflection in the designation belonging to a particular class of concepts. Organic nature, conformance with spelling and language tendencies. Compatibility, or the ability to be combined in terminological combinations. Unambiguity, nominativity, as opposed to descriptive attribute, which is calculated according to this formula. And brevity. Here is an example of the subworded text. The full text of explanatory dictionary on physics, subworded into simple and combined subwords, is available on GitHub. Discussion. The practical implementation of the proposed approach consists, first of all, in training of embeddings for Ukrainian subwords, composed and simple. At the same time, taking into account the significant prior work in creating vector databases within the framework of the traditional approach using word dictionaries, it is advisable to consider the combination of the proposed approach to segmentation based on morphemes with known methods of tokenization and vector embedding of whole words. This can significantly improve the performance of NLP models, including those designed for reverse dictionary tasks. This dual approach allows the language model to track both the semantic nuances provided by morphemes and the contextual information encapsulated in full words. The next object of modification is the stage of vector embeddings, where changes can be made in three important directions. Embedding based on morphemes, which allows displaying the semantic and syntactic properties of vector embeddings for the entire variety of morphemes. Word embedding with morphological awareness, which consists of combining the process of morpheme embedding with the formation of word embeddings, ensuring that the resulting word vectors will reflect the contribution of individual morphemes. Contextual embedding using language models such as bidirectional encoder representations from transformers, BERT, or its derivatives, capable of generating context-sensitive embeddings. Tuning the architecture of the language model covers two main aspects: the inclusion of morphological information in the input layer of the language model, and the corresponding adaptation of the attention mechanism. The learning strategy of LLM-modified architecture is based on joint learning of morphological and semantic tasks. This prompts the problem to develop its representations that are informative at both levels. Transfer learning and fine-tuning procedures can be used to simplify the learning process with the involvement of a pre-trained embedding and the language model as a starting point, with their further refinement on the corpus of text annotated with morphological information. An advanced option for merging different LLMs, which has been intensively developed recently, is to combine their architectures using a special merge kit framework. Its feature is the possibility to obtain the resulting model of the same size and the same number of parameters as in the models that were subjected to the merging procedure. The list of the main methods of this type is presented here. This figure illustrates the process of combining 4 pre-trained language models into one using the dir-ties combined method. In this way, for example, a language model of a physical technical orientation can be implemented. An alternative option for combining models with the embedding of word vectors and subword vectors is to use the switched mixture of experts, MoE, which was developed by the team of developers of the LLM family of the Mixtral type and allows to create highly adaptive models by combining the conclusions from a set of expert subnetworks. The main idea behind MoE is to distribute input data between different expert models based on their specialization. After processing the input data by several selected experts, the results of their work are combined using a switch that determines the weight of each expert for the final output of the model. At the same time, the rest of the experts are not involved. That saves computing costs and allows reducing the requirements for available hardware resources. In the context under consideration, each of the MoE experts is proposed to be replaced by a pair of LLMs, one of which works with traditional word embedding and the other with a vector base of subwords in the appropriate task modality. Using separate experts for processing words and separate experts for processing subword vectors in the context of MoE opens up opportunities to improve the flexibility and efficiency of language models and opens the possibility to involve different levels of linguistic analysis, combining a deep understanding of the morphological structure of language with contextual analysis at the level of whole words or phrases. Combining input from experts specializing in different levels of linguistic analysis can lead to a deeper and more comprehensive understanding of the text. This is especially important for complex language tasks such as understanding allusions, idioms, or ambiguities. The use of these approaches opens up new perspectives for creating more powerful and adaptive multimodal systems that can effectively handle the complex tasks of analyzing, understanding, and generating diverse content. Fine-tuning embeddings trained in other languages is a viable elaboration. It holds promise to benchmark the proposed method against the byte pair encoding technique and establish a gold standard for cosine similarity between dictionary definitions and predicted terms. Utilizing predicted terminology can augment machine translation systems, elevating translation quality. This methodology can extend to other Slavic and word languages. The created subword vocabularies can expand beyond physics to encompass various domains, including general dictionaries. Ultimately, we anticipate the development of a neural network adept at autonomously suggesting terms for emerging concepts, representing an advanced AI technology capable of performing terminological tasks. Conclusion. So, we have introduced a novel method for subword segmentation essential for the pre-processing phase of reverse dictionary tasks and other natural language processing challenges, thereby embodying the principles of terminology science within a machine learning framework. We also have established criteria for term suitability in a format compatible with machine processing and discussed possible ways to carry out machine learning to obtain on this basis a reverse dictionary. The resulting subworded text mitigates errors commonly encountered in widely used byte pair encoding algorithms, which rely solely on mathematical statistics. By employing symptomatic statistical and analytical techniques from terminology science within machine learning, we take a significant step towards executing various terminological tasks intelligently, effectively imparting human-like thinking to AI systems. Furthermore, the neural network trained to autonomously generate terms for novel concepts holds the potential to evolve into advanced AI technology capable of handling all terminological work. Thank you for your attention.